Okay, physics theories, Mr. Thompson here again. All right, page 81. I'm going to skip number 3 and we'll take a look at number 4. It says light travels into an air-glass interface where the index of refraction for the glass is 1.51. If the wavelength of light in the glass is 720 nanometers, find the critical angle and the frequency of light in air. So let's start with the first one. Let's just draw a quick diagram to show what's happening here. And so it has to be going from the glass into air. So it would look kind of like this. So it's moving along here in glass at some incident angle, and it refracts right along the boundary. Of course, I want to make sure I've got my 90 degree to the surface, the normal, drawn in here. Okay, wonderful. So this will be what we call theta c, the critical angle. The refracted angle here is 90 degrees. And the angle where it refracts here should be called theta r, maybe, for example. Now, I like the following, right? Instead of the r and then the c and that kind of thing, we don't really need all of that. I'd rather go with my variables like theta g, okay, and theta a. Okay, kind of helps you keep track of it a little bit better. Now, we know that there's an n value for the glass and we have the n value for air. So to figure out the critical angle, what we do is we realize what we're looking for here is sine theta g, and writing the rest of the relationship there, sine theta a equals na over ng. Notice the g and the a get reversed when we look at our indices of refraction, the ratio there. Now I'm going to go ahead and put in my stuff here. Now sine theta a should be sine of 90 degrees. 1.00 over 1.51 from the question. And so if you think about theta g, whenever you want to try and find a critical angle, all you really need to do is take the sine inverse of the ratio of the indices of refraction. So kind of the index where it's going to over where it's coming from. And so this would be essentially 1 times 1.00 over 1.51, because sine of 90 degrees is 1. Okay? And the calculation. $41.8. Okay, how about part B? We want the frequency of the light in air. Well, we have the wavelength of light in the glass. We can find the wavelength in air. Would be a nice choice now. Otherwise, we have to find the speed in glass, one of the two. So I'll go ahead and find the wavelength of light in air. Now, if you notice the last problem, right? When the wavelength, of course, changes as it goes from one medium to another, did you notice the last problem here that we did, which was question 2? We noticed that the wavelength in air was a larger number than the wavelength in water. Just like the speed is larger in air than it is in water. And so there's a nice easy way to figure out the wavelength of the light in air. And it's really just taking the indices of refraction, index of refraction, I should say, and multiplying it by the wavelength in glass. Okay? Now I can set it up with Snell's law, that's fine, but I'm just saying this is a nice little easy way to kind of see it. And you can do that by noticing what you can learn from some of the previous problems that you did. Okay? Now the frequency in air is going to be c, the speed of light in air, over the wavelength in air. And so 3e8 over 1087.2 e negative 9. Sorry about that, just going to switch the 9 to an 8 there. And I get 2.76 E14 hertz. Okay, I'll come back and do another one in a moment.